All right. So did you run a particular analysis, Tyler, where you came up with estimated marginal means? Is
Yeah, so my MANOVA had two dependent variables, two independent variables, and I had one covariate that I controlled for. Another question I had relatedly was once I put in the covariate, I couldn't run the post hoc analysis. So I was
right.
curious, is there, obviously I can't do that, so is there a way, like,
Is that where you had to click save or options?
Now I'll show you. If you look at the videos, you'll see how I did it in the videos. There is
Option.
there's just a different way that you have to do it when you have covariates. But I can show you again um, this afternoon, so we'll have that. So we'll do that. I'll get to that. But before I get to that, so estimated marginal means. Somebody take a stab at broadly what are estimated marginal means.
So because we're using multiple DBs, we create an omnibus variable that is essentially all of those combined in a complex process, but they're combined. And your estimated marginal means are not the means of those particular variables, but of that omnibus variable. And so they're a little hard to, they're not hard to interpret, but they're a little different because they don't fall on the particular scales you've already used, and instead they are an estimate on that omnibus variable, which is a outcome of the process. Or my way out.
Not way off for sure, and maybe onto something that I've just never has never surfaced for me before. But estimated marginal means, as I've used them in the past, are the averages that take into consideration the covariates that you have in your analysis. So it makes an adjustment for those covariates. So setting that covariate at some, probably the mean value is most traditionally what we do. And so if we set your covariate, what was the covariate that you used, Tyler?
um, cultural worldview.
So if we set cultural worldview at the mean for everyone instead of the variability that it has in the real world, if we just say, in theory, if everybody had the same score for cultural worldview, how much would that adjust our dependent variable? And so those adjustments are that's what the estimated marginal means are. And at the bottom of the table, you'll see a note that indicates that these means were adjusted for, and it will list out your covariates, and it will list out the value that it held the mean to, or that covariate to, which it's always the mean. I think you can change that, but you have to use some SPSS syntax to do that. So I think what Chris was saying is there is that sort of omnibus calculation that happens in the background, although I just don't know that I've ever requested or have seen some omnibus average. So if I'm missing something there, I'd be happy. It'd be new information for me, and I'd be happy to learn about it. So that's estimated marginal means. But we also, well, the other thing I would note, SPSS isn't particularly careful when it labels the tables. In some cases, it labels tables estimated marginal means when they really seem to be just marginal means. They're not estimated, or if they are being estimated, it isn't particularly clear why they have to make some estimation, because it's just for some group that's a part of the data, and the mean should surface from just calculating the mean for that group. But I assume that naming convention follows some logic that SPSS or IBM has used, but it's a little, I'm a little uncertain what it is. But for sure, if you see the note at the bottom of the table, then you'll know they've been adjusted for your covariates. If you don't have any covariates and they're calling it estimated marginal means, then I'm not quite sure why they're not just marginal means instead of estimated marginal means. Again, if you can help shine light on that for me and perhaps your classmates, I'd be happy to try to um, improve my understanding there. So, and then getting to the last thing that Tyler asked, let me see if I can get SPSS. And just it is true when you add covariates to your data. When you add covariates to your data, that so it's this block here that becomes, you can't even click on that block because that post hoc button is grayed out. And so the way that we work around that, I think this is about the analysis that we did. And so grayed out, what you can do is under options, if you say that you want the display the means, and even up here it's called estimated marginal means. Clearly there's something going on there that they're estimating something, because this box, even if you don't have covariates here, that still is labeled estimated marginal means, I'm pretty sure. It's still labeled estimated marginal means. And so I don't know what it's going to be estimating. So maybe I could read the help. That might help. And but I haven't. I have not done that. So let me add in these couple variables. Grayed out. So we want to do options, and we want to do. I want the means for everything, and I want to compare main effects, and I want to do Bonferroni correction, or I want to do Seidel correction, or I don't want any correction. So you just pick one of those, and this will produce the output as you would sort of expect with those corrections. With those corrections incorporated, and so it would be, and I said least significant difference, essentially no correction, and I could get that from this table, which is the same table as we would have gotten if we would have not had the covariates. It looks exactly the same. Other questions? Did that help, Tyler? Other questions? Brittany?
On that note, and I know we probably have, so like yours is like sex and sex, it has male, female, like across it. Because I know on the other one we would just read like one to one and then one to the other, but on this one it has like male and female both in the same line, right?
Yeah, remember the other one, it reports everything twice,
Okay.
and that's just what it's doing here too. If we get rid of the covariates, and I'll just show you once. If we just do analyze, we'll go back to something that might be a little bit more familiar, just the univariate case, and we will do. We need to have something that has more than two groups. I'm going to do this, and if I do post hoc, and then do this. So this should sort of look like what we looked at a couple weeks ago when we looked at ANOVA, where in 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 all of these cases, everything is reported twice. So here's married and widowed, and I also have widowed and married, which would be the same absolute difference. The sign is different because in this case it's married minus widowed. The mean difference is minus 0.14. Widowed minus married, of course, the mean difference is going to be in absolute terms the same, and the significance level would be the same for both of those. And so that's why it showed male and female, and then on the next line it showed female and male. And I think if I use this same dependent or independent variable, it would look very similar to this table even with MANOVA. Does that help or not?
Yes, I was just trying to answer your question when you asked me if the males, that small group was significant, and I was like, well, it's comparing. I was trying to find the chart that I'm looking at for that. But yeah, so that makes sense.
Other questions?
As covariance, I chose 6 and 8 and 3 are higher. And then 8 and 6 is only the variable, and 3 are higher is continuous.
Is age a nominal variable?
Age is continuous.
What's the other variable?
6 and the 3 are higher.
What's the third one?
3 are higher.
And is that nominal or continuous? Yeah, so they would all be, so no nominal variables. Male and female is a dichotomy, right? So that's just, yeah, so if it's, as long as they're either dichotomies or continuous variables are just fine. If they're nominal, more than 2 levels, nominal with more than 2 levels, then we have to dummy code it if it's going to be a covariate. Other questions for homework number 6?
So when I'm putting in, I have 3 variables for my graph. When I'm putting in these variables to the graph, does it matter necessarily?
You have 3 independent variables?
Yes.
So you're doing a 3-way MANOVA? Just do a 2-way. Don't do 3. I wouldn't do 3-way.
Okay.
You could do a 3-way, but you just would have to create separate graphs. So that would be where you'd put the third variable. You'd do one on the x-axis, another variable, another one of your independent variable on the y-axis, and then separate graphs for the third independent variable. But for this assignment, just do 2-way ANOVA because I'm reasonably confident that I probably wouldn't want to take the time to try to interpret the 3-way interaction, and it adds a level of complexity there that we just don't need for our purposes. Other questions?
I just wanted to understand for continuous, because I think our covariance here was not nominal.
Which one?
In the previous.
Nominal, but it's just dichotomy, right?
Correct, dichotomy.
Yeah.
Yes, I meant dichotomous. But you said it's okay to have a continuous covariance?
Yeah.
How would that sort of interpret out?
How would it what?
How would we interpret it out? How would the table look in a sense?
It wouldn't. So for the covariates, we don't get group means.
Okay.
We would get, and Brittany had this with the analysis that we were looking at. You'd have a significant or maybe it was. Maybe you had this significant covariate?
Yes, with gender.
Okay. Yeah. And so you have a significant covariate. You really don't understand from the MANOVA analysis, is males higher than females across your different dependent variables.
Okay, that's what I was saying. So
yeah.
That was me too then, I guess.
So that male and female was a covariate or an independent variable? If it's an independent variable, you definitely have the means for male, means for female across all of your dependent variables. If it's a covariate, you wouldn't necessarily get all of those, and And that isn't the focus of the analysis anyway. You're just wanting to control for that, and you're probably not interested per se in are males higher or lower on your dependent variables. If you were interested in that question, you probably would have that as an independent variable, and maybe even a three-way interaction that you would do, or three-way ANOVA that you would do if you were really, really interested in it. Does that?
Yeah, I was just wondering if for continuous covariance, how would the table kind of appear? Because we would have.
There would be no table. You would see a significant. Let's see if I can go back up here and tell you what I'd be looking at. So if we start with the omnibus effects, and so in this case, age is a continuous covariate. Sorry, you can't read this very well, but this covariate is age. And so in this case, I would know that age was a significant covariate. In other words, it made a meaningful contribution to. It adjusted the means in a meaningful way. I don't know what from this. I don't know as age goes up, does the dependent variable go down, or dependent variables in this case go down? I don't know that from this. I'd have to do a separate analysis if I was interested in that. Which you could just correlate age with your dependent variables, and you would understand the relationship that you'd have between the covariate and your outcome. So this would be the first step where we look at the omnibus effect. It is significant. So if we then just took that to the next step, well, for which of our dependent variables, in this case I had 4 dependent variables, again you can't read this very well, but this is age. For which of our dependent variables was it significant for? And I can see that as significant for how the respondent feels towards African Americans and how the respondent feels towards Hispanics, and not for the other 2 questions or the other 2 dependent variables. And so from there, I would, again, I'm still left, I don't know what the nature of that relationship is. This doesn't tell me that, but nonetheless, I know that there's some relationship there.
And for the homework, because he said it's okay to have just look at one covariate, 3 DBs and 1.
And did I say use covariates if, I didn't say you necessarily had to use covariates, did I? If appropriate.
Okay, because I just have one that.
Yeah, and you don't have to make up a covariate to use if you don't have any, if there's no need to have any in your analysis, that's just fine. You don't have to, it's not a necessary.
And you were saying that they have to be done because, so like you did education, like.
Education is continuous, it's years of education. So it doesn't, if it's a nominal variable, just like regression, just like independent variables for regression. If it's continuous variable, it will work just fine.
Okay.
If it's nominal with more than 2 groups,
Like race.
yes, assuming you have more than 2 groups,
Yeah.
then you'd have to dummy code that into k minus 1 groups, k being the number of groups that you have through race variable. And you'd have to do that in order to use it as a covariate. Does that make sense? Other questions? So maybe because we're sort of at that part of the semester where, have we covered a lot this semester? Have we? No, I don't know. We have a couple more days. I don't. Do you feel like we've covered this? This is only moderate, right? In terms of a workload, this is moderate, right? You've had classes where you have to do a lot more work than this class.
See, I'm still like.
I think we covered a lot of breadth.
Sure, we haven't gone right. So if we did a class that was just ANOVA, we could spend
Forever.
right. So or a class just on regression, or a class just on structural equation modeling.
Which
We-
ones we do have that class now.
The structural equation modeling, yeah. And I think you'd be able to find it in an ANOVA class on campus somewhere. You'd be able to find a regression class on campus, or at least a couple different regression classes. And so we definitely did more breadth than depth. So what was I saying? So what I was saying is that if we wanted to, let's say we wanted to answer the question that Pavitra had, that is, what's the relationship between the covariate and my outcome variables, my dependent variables? A pretty easy way to do that, in a way that I would probably go about doing it, is under options, you can say parameter estimates. And when you do parameter estimates, they're the B's that we get from regression analysis. And so it does do what it does do is it dummy codes up all of our independent variables for us, and then it comes up with the parameter estimates, or the B's. And so if age was the variable that we were interested in before, and so this is the covariate age, these are the parameter estimates, and I can see that the B is minus 0.15 for the first dependent variable, which is one of the ones that was significant at when we looked at it a few minutes ago. Anybody remember how we interpret B's? How do we interpret minus 0.015?
For every year age goes up, the attitude towards African American goes down 0.015.
Yeah, very good, perfect. And so this would be that analysis that you could a quick way. It's also a quick way. Let's say you wanted to run regression. You wanted to do a regression analysis, but you didn't want to take the time to dummy code all your nominal independent variables. This would dummy code it all for you. It might not do it exactly the same way that you would do it, because it just makes one of the groups the implied group, and it also includes all of the interactions. If you were going to do regression analysis, you might not be interested in all of those interactions, but nonetheless, it's useful. It can save you some time especially if you're doing data exploration. You just sort of want to understand your data as you're looking across different dependent variables and independent variables that might be covariates or otherwise. It's just a useful tool to have in your tool chest to be able to do that. So no other questions on homework 6? Let me look at it one more time to make sure. At least 3 dependent variables and 1 or more covariates if needed. Somebody asked me, should we include a table of all of the means? No, but when you write up the paragraph that reports your results, if you have significant results, you should report means for the significant results, right? Does that make sense? And anytime, what are the 2 things? What's the one thing that well, maybe you've learned at least 2 things in this class. One thing is small effect size is how large? Or how small?
0.01.
And medium is? It's not 0.03?
No, it's not.
Okay. And then large is 0.25, right? So everybody's learned that. Everybody has learned don't do p is equal to 0.000, right? P is less than, so you've learned that. The other thing, I don't know that I've made this another pet peeve, but never report an average without a standard deviation, right? It should be, if you're reporting an average, people that work with data expect and want standard deviation. So never report average without standard deviation. It would be sort of right in the same. So if you do report a table or do have to report some means, make sure you also report standard deviations.
When we get the estimated marginal means, they don't come with, and they are, there's a standard error with them, not a standard deviation.
So yeah, so you wouldn't have, you could, so what would I do in that case? We could convert standard error to standard deviation, but it's more work than it's probably worth. I probably would report just the standard deviation, but it's not an estimated standard deviation, with a note in the table that these are estimated marginal means based on the covariates, but the standard deviations are the group standard deviations, and I think nobody would quibble with that. So
I would report which ones again? The regular
report the estimated marginal means and then the regular group standard deviations
deviation,
with a note.
With a note stating this is
Yeah,
the
yeah,
standard deviation pertaining to the. Okay.
yeah. That would be probably the most straightforward way to do it. Good. So no questions on this? All right. And Pavitra?
I just, for one of the movies that I've read in the past, they reported the group means and the standard deviation. Is the group means and the arguable reported?
Um,
All three, I mean, that's just.
so they reported the group means and the standard deviation. And what else?
No, and then they reported everything else in text, but they had the table with the group means and the standard deviation.
Yeah, that would be you would always, if the results were not significantly, if there were not significant differences across your groups, then reporting the means might be somewhat optional, because whatever they are, the differences aren't meaningful. But if the differences are significant, then it's no longer optional. I think you actually have to report the means. The group means, right. So
We would never report all three,
what's the third one?
like the estimated margin.
Probably, I can't think of an example where it would make sense to do that. If you used covariates, I would always report just the estimated marginal means, because that's what the significance tests are actually based on. Those means, not the group means that don't take those into account.
So is it okay to think about it this way, that for MANOVA, we're focused on if we have significant differences, group means and standard deviations, but for MANCOVA, it's estimate if we have significant, the estimated marginal means and the group standard.
Yes. Yeah. In both cases, the standard deviations would be the same, right? It's just going to be the group standard deviations as opposed to trying to convert standard error. Try to convert. I think it would just be to convert the standard error to standard deviation. It's just because standard error is standard deviation divided by square root of n, so it'd be just times n squared. So you could take the standard error times n squared, should give you the standard deviation. But I think I would still be more comfortable using the actual group means with a note. Okay, so I'll look forward to getting that a week from today, right? So there should be a couple different files that we're going to look through for confirmatory factor analysis and what's that? What about it?
Are you going to have it on Wednesday?
I could have something on the take-home exam. That would be, yes. I won't have you do a confirmatory factor analysis or structural equation modeling, but there might be some another question that would have you apply these skills. Likewise, what we talk about next week with mediation and moderation, there could be, I won't have you do, because we don't have a homework related to it. And there could be something in class, in the in-class exam as well. So, good question. So we're going to really the focus here is more on looking at some examples, being able to read both confirmatory factor analysis models and structural equation modeling. Having a better grasp when you run across that kind of analysis in your reading, you'll hopefully be better able to understand and evaluate that work. In terms of actually doing the analysis, I'll show you a quick example. That's what the very bottom example is. I'll show you an example of a model, and SPSS doesn't do it, so we have to use some different software. We'll get there before the end of class. But I think at the end of the day, it wouldn't be beyond what any of you would be capable of doing, if so motivated to do after this class, to do that same kind of work. It's not some black box that only those that have some special skill can do. It really is. It's pretty straightforward. It might take a little bit to sort of get the syntax right, but then you should be good to go. And then we may as well talk about it now. SPSS or IBM does have a program called AMOS that would allow you to do. You can sort of create the model on the page and test it. I've never used it. Well, maybe I tried it a couple times, and I got so frustrated with it that it didn't seem like it was something I wanted to spend time on. And I probably had a pirated version from someplace that only halfway worked anyway. But that would be an option. Listerol and the department used to have a license code that they shared rather liberally for Listerol. I don't know if that's still the case or not. Not the case anymore.
So yeah, as it sits, I only because I took you have to get someone to log you into the computer in the grad lab in order to get access to Listerol.
Well, so that's another option. We're going to do it with our statistics, which would be the free, don't have to pay anything, and gives you exactly, if not, I mean, they're just. But those options would be there. But for both of those options, I don't know that the learning, you'd have to learn, if you've never used either one of those tools before, you'd have to learn as much to use those as you would to do the example that we're going to talk about in R. And so, but if you've used Listerol, you sort of understand the syntax, and so that might be an option that would probably make a lot of sense for you, because the last thing you want to do is have to spend, weeks doing your analysis. You'd hopefully want to get that done rather quickly so you can get things written up and get it sent out. So so a little ahead of myself, but if we just looking at these kinds of diagrams, there's only less than a dozen. What do I have? I have 3, 6, 7. I have 7 different, the notes on the bottom, 7 different kinds of elements that appear in these models, and they appear, this is everything. And so not every model will have all 7 of them, but many models will have, most models will have all models have some subset of these. They might only have 4 of the 7, or 5 of the 7, or maybe only 3 of the 7. But we'll just sort of look at each of these elements, and again, will help us to process examples as we move forward. So not in any particular order, other than the order that seems to make the most sense. The blue rectangles are measured variables or observed variables. And so P1 through P3, That's a measured. I have a vector of data in my data set that's called P1. I have another vector or column that's called P2 and another that's called P3. And I have the same for the Qs. And then these are also observed variables. And so the blue rectangles are your measured variables, things you actually have data for.
Okay, so do you restrict those for things that you've actually like counted, like for instance in an experiment, or do you, like you're doing a survey, like you would never have a blue rectangle because you haven't actually physically like counted it? Does that make sense?
One more time,
So like let's say you have somebody's communication competence, right?
Yeah.
So if you have 3 experts observe them and rate them on a scale, then that would be a blue rectangle because that's been observed. But if you have them self-report their communication competence, that would be not a blue rectangle.
no, that would be all. That would be whether it's by observed. It's that might be the word that's thrown you there. It's observed could be somebody self-reporting some data for us on themselves, or it could be some observer watching them and reporting some data for them. So it's using the word observed a bit more broadly, I think, than you are. It's any measured variable where you have data for it would be in this model a blue rectangle. Does that answer your question, William?
Yes.
Okay.
So I just wanted to double check on the same thing, that it's basically none of those variables that I would have computed from my observer. So it's basically,
Give me an example.
if I collect a set of questions on, I'm trying to create my own scale, on a couple of variables in order to create a scale. And I put 2 questions from somewhere, 2 questions from somewhere. I have 4 questions, so each of the 4 questions would be the blue. And if I added 2 questions up and created a variable, that would not be the blue because I computed it. I didn't observe.
That in some cases the 2 questions that you added up could be a blue, and we'll talk a little bit about that. But in most cases, the blue rectangles would be like these might be your how many questions for I've asked you this this one thing I haven't learned in class. How many questions in the communication apprehension? 24. So if we were using that scale, how many dimensions? How many? 4. 6 questions for each. Yeah, and so we probably let's say this was one of the what's one of the dimensions?
Dyadics.
Yeah. So how you do your competency in communicating interpersonally, dyadically.
Right.
So that could be we'd have six measured variables that represent that latent variable dyadic communication competence.
Apprehension.
What is it? Oh, it's apprehension. Oh, yeah, no wonder I never did it. So observed variables could be single item questions, could be several questions that you sum together in some way and or average together. Usually you wouldn't put those here because there'd be better ways to treat those, but there'd be no reason why that couldn't be the case. And so we collected this data that has these observed variables, and we have this model of how we think these variables should function together. We think that these 4 variables that create this latent variable should cause this thing to change. Likewise, these 3 observed variables that make up this latent variable also causes that thing causes this thing to change. And so that's the straight arrows or causation. Some people call it used to be called much more often causal modeling. I don't see that name very often anymore. Usually it's structural equation modeling. But if you look at older literature, people call it causal modeling. Of course, if you have only survey data, if you have only data that is at one point in time, it really doesn't get you any further to understanding the causal, or it doesn't. It's not particular. Just because we call it causation doesn't mean that it represents causation. It really is looking for a relationship. It's looking for a relationship. It just happens to be that we think these are causal, so we use straight arrows in the structural equation model that we're building.
Is it more directional? We're saying that green leads to brown.
Absolutely. We're saying this causes this as opposed to this causing that. And you can build models that would have arrows going in both directions, because we think this causes this, but we also think that this causes this, which I think in a lot of cases is probably true. This particular model doesn't have that, but you could do that for sure.
We're not establishing, I mean, we could in some instances, but we're not really saying causation, like you said, even though we use the word.
Yeah, and but you are implying that when the two-headed arrow is implying correlation. We think that these two things are correlated, and it makes sense that the two would be if this causes this and this causes this, then these two almost necessarily, if these two are true, then this correlation also has to be true. Just because it just cannot be in any other way. So straight arrows are causation. With a single point on it. If it has two, if it's a curved arrow, it's denoting a correlation. The green ovals, I don't think they're circles, but the green ovals would be our latent variables. And so we think these four questions, these four responses make up this latent concept, whatever that is. We can't measure this thing directly. We measure indirectly through these four items, or through these three items, or through these five items.
So is that kind of like what we did when we did the exploratory factor? Now, like we got whatever those blue rectangles were to see if they loaded on the same thing to make one green.
Yeah, the coefficients, the loading coefficients would be for each of these arrows, there's a coefficient that designates how strong the relationship is between here and here. That would be the coefficients from that table that you look at. So it's very similar. The difference being when you're doing exploratory factor analysis, you might throw all 11 of our observed variables into an exploratory factor analysis, and then just let the math be the math and sort of see how those things load at the end of the day. Here, it's much more confirmatory. We have some reason to believe theoretically that these four load on this, these three on this, and those five on this. Okay. Does that make sense? Mm-hmm. So straight arrows are causation, curved arrows are correlation. Blue are observed variables. Measured variables would be maybe a better anything that we measure. Latent, green is latent independent variable. I guess I do have latent dependent variable. as brown. Still an oval. But it would be a dependent variable, right? We think this is the independent variable that's leading to our values on that dependent variable. The red circles are indicators of error. And so for each of these arrows, as I mentioned before, for each of these arrows, we'd get, when we do the analysis, we'd get a weight, like a regression B coefficient, or it could be a standardized coefficient between -1 and 1, or you could get, they could be B's as well, which would take on a value that's relative to the scale that you're using. So for each of these, we'd have a weight, a B or a beta. Same way with our error terms. And the error terms just indicate, indicate what percent, at least abstractly the way to think about it, what percent of our answers or responses to this question seem to be noise, as opposed to not noise or signal. And we use the error term allows us to extract that noise out of that relationship. Think about when we calculate alpha reliability. When do we do alpha reliability? Somebody give me an example of when we'd calculate alpha.
See the relationship between, for example, P1 to P3, how well do they come together?
Right. How about has anybody
Use it to measure your scale reliability to see if your items in your scale actually measure what you're intending.
right? So it's an assessment of reliability. Reliability is consistency, right? And let's say your reliability is 0.85. That's a decent number, right? So that means 85% of the signal is 85% of the variability is signal, 15% is noise. That's the way that's an interpretation of that. If your reliability measure is 0.85, 1 minus that would be not reliable or noise. And so that's what we're pulling out when we generate these indicators of error. And so one of the values of structural equation modeling is it allows us to assess the relationship between this latent variable and this dependent variable after we remove the error. And does the error, would error, if we remove error, is our relationship going to be stronger or weaker? Yeah, it will always be stronger, right? Because error is just noise, right? And so if we remove the noise and only have signal left, we're going to be left with greater signal because the noise is all gone. And so, what's that? Yeah, because we take all of the unreliability out of the analysis, and we're able to assess the relationship between our independent variable and dependent variable absent that noise. And so that's always been one of the nice features of structural equation modeling, is that it allows you to make that assessment absent measurement error. If you have too much measurement error, you'll never get your model to fit. We'll talk about fit shortly. You'll never get your model to fit though. So it's not a fix-all. If your reliability is 0.85 that probably will fit pretty well. But if your reliability is 0.45, not reliable, pretty much just random noise, there's no way that you're going to get that to. It won't fit into a structure that looks like this. You wouldn't get it. You could tell the computer to see if it fits, but then when you assess the fit, it's going to say no, it doesn't fit. And so that ability to examine the relationship without error between independent and dependent variables, or between your, likewise, this correlation between the two independent variables that we calculate here would be the correlation absent the measurement error. So, and there's only so much we can do there in terms of removing error. You can't garbage in for sure, garbage out. So, Rachel.
A couple weeks back, you were mentioning about how if like the alpha is really high, that indicates we might almost be having the same measure. Like if it's a 0.95.
Yeah, if so.
If we have it too high, would we just remove one of them and just have the one, and then do the next steps of the error and so on?
Yeah, I think if somebody, I always get a little bit suspicious, and I'm always a little worried if the scales that I'm working with have too high a reliability. Let's say the reliability is 0.95, I wouldn't lose too much sleep over it. 0.99 suggests to me that there's probably, that you'd have to look, and each situation could be a little bit differently, but it would seem to me that there probably wasn't a whole lot of variation in how your respondents answered your questions. So if they put 1 for the first question, they put 1 for the second, they put 1 for the third, and 1 for the fourth. And so that would be the fear that I would have if it's too high.
So it's not, we don't necessarily need to worry about the variables themselves. It might be how the respondents are
It could be that, or it could be the questions that you're asking are confusing and people, or you're asking people to do. So yeah, it could be some combination of the variables themselves or the methodology. The only one that I don't think I've said anything about is, so we have error terms here, but we also have an error term for the latent dependent variable, and we call those, that's called the disturbance usually. And so far so good. This is a correlation between, we think that think of the error term as residual, might be another, remember what's residual? Difference between the
Actual minus.
yeah, so think of error terms as in some ways being the residual, and in this case we think that these two residuals are correlated, and so we're going to add that correlation into our model. I think usually when that happens, it's not because we have a theory or a hypothesis that would state that these two error terms should be correlated. Usually it's probably because just in diagnosing the model, we see that it's not fitting particularly well, for example, and we can look at some diagnostics and see that, well, if we correlate these two errors, the fit will improve. And some people would have all sorts of issues with that, because it really is a confirmatory process, right? It's not a data exploration process. You build a model a priori based on theory, and then you test that model to see if your data fits that model. Does the structure of your data at all represent the structure that you have on paper? And that's sort of the textbook way that we do structural equation modeling. Sort of the add-on to that would be, well, what if it doesn't fit? Then do I just have to throw everything out and start over again with another set of data that might try to improve on that? Or can I make some adjustments? And again, you'd have a lot of people who would have issues with that. And if you report all of those adjustments in your manuscript that you did, good luck getting it published, right? You might, but you might not either. And so it's just one of those things that we should be aware of. That again, the idea would be drawing a model out. This is how I would do it. Draw the model out based on theory and what I think should happen. Then write your data and write the code to test that. And then hopefully everything fits well. If it doesn't fit, then you'll have a series of decisions you need to make in terms of how much fiddling are you willing to do with the model. In my experience, there's a fairly high threshold for everybody that I work with in the past does a lot of fiddling. It doesn't always get written up that way though. Not that they say they didn't fiddle, but they don't tell you they did fiddle. It is what it is, and you'll just have to sort of develop your own understanding and tolerance for using a tool like this to do exploratory work. So then a couple other things in the note on the side. So we have the measurement model, which would be part of the measurement model. This latent variable and these 4 observed variables, that's a part of the measurement model. This is a part of the measurement model. This is another part of the measurement model. And then we have the structural model, which are the path. This path is part of the structural model. This is another hypothesized relationship. And then so is this correlation. So those would be parts of the structural model. This correlation would also be a part of the structural model. And so you can break your model down into the parts that are measurement and the parts that are structural. And then we have exogenous variables and endogenous variables. And an exogenous variable is a variable whose variability is assumed to be determined by causes outside of our model. That's exogenous. Endogenous, the value of the variable, the variable whose exogenous variables are variables whose variation is explained by other exogenous variables that are inside the causal model. So this latent construct here would be considered exogenous because it's not being caused by any other features in the model. Its value is not being influenced by any other features in the model. This latent construct would also be exogenous, and then this would be endogenous. Does that make sense? And so we'll look at some models here this afternoon, and that's one of the things that let's make sure that we are all on the same page in terms of what's exogenous and what's endogenous. And so just one last point. We talked early on in the semester, and I know that I made the point that structural equation modeling is a mixture of factor analysis and regression. And the measurement part, I'll start there. The measurement part of the model is the factor analysis part of the analysis, and the structural part of the model would be the regression, the part that's related to or closest to regression. So for whatever that's worth. Questions? Comments? So I have three different models that we'll look at that are all variations that all include elements of this, but look and behave slightly different. This is from a publication that Mike Stevenson and Lance Holbert did back in 2003. And the first approach would be just all of your variables could be just observed variables. So this has only rectangles, right? Rectangles are all observed variables, and so we only have observed variables. These observed variables could be just single items, male or female, age, education, or they could potentially be composites. It could be communication apprehension, and I'm doing the average across all items for that scale, and that's the observed variable here. So it could be either of those. So what's exogenous and what's endogenous?
In this model,
Yes,
that one.
that one is endogenous for sure. What's exogenous? Everything else?
Right, the first three are exogenous.
Yeah, these first three for sure, right?
Okay.
Because we're not theorizing that these are influenced by. These values are not influenced. There's no arrows pointing to these, so we're not hypothesizing that the value that they have is in some way influenced by the model. So no arrows pointing to them indicates that they're exogenous. Arrows pointing to this one,
So it's endogenous.
it's endogenous, yeah. But this one here functions both as an independent and dependent variable, right? Here from here to here, it's a dependent variable, right? And then from here to here, it's independent variable, right? And so we could use structural equation software, any of the variations that we talked about earlier, and you'd be able to do this kind of model and assess whether your data fits this structure or not. And that word "fit" takes on a particular meaning, and there's a number of different ways that we assess fit, but you would easily be able to do that. We could also do this if we wanted to do it with just regression. We could do the same analysis with just regression. And so we'd have to run two different regression analyses. And the first one, this would be the dependent variable. And these three would be independent variables. We'd get the b or the beta, and these paths, that would be the that would be the magnitude that you would associate with each of these paths, the B or the beta from the regression analysis. So that would get us these three, and then in order to get the relationship between here and here, this is the dependent variable, right? And then everything else is independent variable, and we only care about the relationship between this variable and this, between this independent variable and this dependent variable, and that would be the coefficient. We're not hypothesizing a relationship from here to here. We hypothesize a relationship from here to here and then to here. And so in that second regression analysis that we do, this is our dependent variable. These four are our independent variables. We're not hypothesizing any relationship between here and here. We're saying it's zero because no path just indicates that we don't think there's a path there. In other words, the path is zero. And so we don't care about the weights. In that last regression analysis, we don't care about the B's for these three. We only care about the B for this independent variable and this dependent variable. Question?
So just to be clear, the 3 boxes on the left would be the factor analysis part of it, how these factors compose of this one variable, the middle box.
No, this is really only the regression. This doesn't have both of those components, and so that's a good clarification that structural equation modeling can have both factor analysis and regression, or it can be just factor analysis, and then we'd call it confirmatory factor analysis, or it can just be similar to a regression analysis, and that's what we have here. So there really isn't a factor analysis component that's taking place here. Does that answer your question? Other questions? Perfectly acceptable, probably not all that common. Older literature that you'd read, you'd find it more likely than more modern communication literature in my sort of anecdotal read of literature, but so that would be the observed variable approach. Second approach uses it's not a trick, but uses an idea that we talked about just a minute ago, where and we call this a latent composite model. So we have these 3 exogenous variables, model, and we say that they predict this endogenous variable. These 3 exogenous variables predict this endogenous variable, and then that predicts or causes our second endogenous variable. So very similar, other than in this case these are ovals and not rectangles, so they're not observed variables. What they are is it's a composite. So this would be an observed variable, or actually it would be a composite. That's why we call it latent composite. It would be a composite that would take several items and make a composite. So it could be communication, apprehension, scale, that we would take the average across all questions for each individual, and that would be this observed variable that we have here. And then we fix the path between the latent variable and our observed variable. We fix that path to 1, and then we set the error term equal to 1 minus alpha reliability times the variance of our observed variable. And so it's just a way for us to use a composite scale and also take advantage of the ability to remove the air from the air variance from the analysis. And that's what this little bit of magic does for us. And the alpha is the alpha reliability, right? So in the example that we used earlier, let's say the alpha reliability is 0.85. 1 minus 0.85 is 0.15. So 15% of the variability is noise, and that's exactly what we're going to fix the path, that path to.
So is that why the other model isn't used that much anymore, because it didn't have the little noise thing? Is it just not as thorough without the?
Yeah, and this is used probably slightly more. My friend Michael Pyle was a big fan of. If you read any of Michael's he used structural equation modeling some. He almost always used this kind of model, and so it's probably one reason why this is probably slightly more common than the previous one that we saw, but it's not. You don't see it all that often. But I think it probably is slightly more common than just the observed model approach. I do say that this model is utilized least in communication research, and that actually came from that Stevenson and Holbert. And so when they wrote that article, they actually analyzed several decades of communication research. I don't know if that holds true today. That data was collected almost 15 years ago, and so it may have changed some. So just another approach. So we can just do observed variables plus a couple latent variables where we're removing air. I would say, if it were me, or I would say I would probably use this approach. I would probably use this approach if I couldn't get an approach like this to fit the data very well. So let's say I used an approach that looked like this, and I was having problems with getting my data to fit. If I instead took these 5 questions and made them one vector of data, one measurement, and calculated the reliability for the 5, calculated the variance for that one newly created variable, I'm much more likely to get the data to fit the model. And I would be reasonably comfortable. I would be comfortable saying, tried this approach, couldn't get it to fit because there's maybe too much correlation amongst the error terms, and so I then tried this approach. And I think I'd be comfortable making that argument. And in this case, we just don't have all of you'd be more likely to be able to fit the data to the model because we don't have all of these individual items that all have error terms associated with them that can cause problems with potential fitting. So the third approach would be similar to what we looked at.
Just a question about the hybrid sort of observed variable approach.
This one?
After looking at the second one, there's no error for any of the observed.
There isn't, yeah. Yeah, there's not, this is just the relationship between this observed variable and this observed variable with error attenuating that relationship. And so then the third approach would be a hybrid model. And so we have some directly observed variables here that are all exogenous. And then we have this endogenous latent variable that is made up of these two items, plus you. And then this also endogenous variable that's measured by these three observed variables. And then, of course, the advantage we'd have here is that the relationship between here and here, we know would be, it would be the true relationship after we remove the measurement error. Here, we're not removing measurement error between here and here because we're not removing the measurement error that we have here. But between here and here, we removed all of the measurement error, so we would have some confidence that. So this would probably be the most typical. But if you pick up a journal article and see a structural equation modeling, you might see something that looks like this, or maybe it might be absent the observed variables here, and so this would be you might just have this and this, and maybe a couple other pieces added to it. Questions? So now I just have a few examples that we can look at. One of the things to think about as you're reading literature that uses structural equation modeling, or as you're doing your own research where you use structural equation modeling, the picture has to be pretty, I think, if you expect to get it published, right? It looks like a spider web that nobody can interpret the relationships. You might get it published, but if it communicates to the reader in a much clearer way because it's a more parsimonious understanding of the phenomena, you're going to have it's not news to any of you, but if you're able to do that, you're going to be much more likely to get your work published. And so keep in mind as you build models, don't make them look like, if you draw them out on paper and they look like spider web, then that's going to be a problem. You probably will never get it to fit very well, but even if you do get it to fit very well, it's just difficult to convince readers that is that because they won't understand it, right? Unless they are going to spend the whole afternoon trying to understand it, and it's unlikely that they're going to do that. So keeping models simple is and some of it is. It used to be that I think I probably did this one. I probably did this in PowerPoint because you can make the. But if you're an Apple user, there's a piece of software called. It's not free. There's a piece of software that does. Engineers use it to do a lot of to make flow charts and engineering diagrams. What's it called?
Visio.
I've seen Visio. That's a Microsoft product, right?
Yeah, but they also have an Apple version.
Do they? That's not the one. It's Gaffle, I think. Graffle, Graffle or EL, is the one that I've had a license for in the past, and it would allow what's that? What is it? I've not used that one before. So there's probably a number of different pieces of software, and if you're going to do a lot of this kind of work, it's probably worth investing in those because your ability to make these pretty is going to be somewhat contingent on the software you have. If you're stuck with PowerPoint, and this is pretty straightforward, so PowerPoint does just fine. But as you work with something more complex, it becomes more difficult to try to manage that with PowerPoint. So let's take 15-minute break, and then we're going to look at a couple of examples of both confirmatory factor analysis and structural equation modeling, and then I'll show you an example of some analysis.